Hubble reached orbit with a mirror polished exquisitely smooth, and precisely into the wrong shape. On June 27, 1990, NASA faced a brutal conclusion. The Hubble Space Telescope, launched only 2 months earlier, could not focus as designed. Its 2 imaging cameras showed the same signature, a bright point surrounded by a broad halo. This was not an atmospheric shimmer. Hubble was above the atmosphere. Nor was it a camera-specific fault. The shared optical system was sending light to more than one focus. A flagship observatory built to see the universe with unprecedented clarity had arrived in orbit with blurred vision. The surprise was not that the hardware had been made carelessly. The primary mirror was extraordinarily smooth. The deeper problem was that a precision test had repeatedly guided the polishing process toward the wrong answer. Hubble is a reflecting telescope. Incoming starlight strikes a 2.4-meter primary mirror, reflects toward a smaller secondary mirror, and then travels to its scientific instruments. The primary is not a simple spherical bowl. It has a carefully calculated aspheric curve intended to bring rays from different parts of its surface into a common optical system. NASA's investigation found that the finished mirror was too flat away from its center. The wavefront error was about 0.4 wave root mean square at a wavelength of 632.8 nanometers, roughly 10 times the specified tolerance. The phrase spherical aberration describes the effect. Rays meeting the mirror at different radii did not behave as one coherent focus. In plain language, imagine trying to gather rainwater with a funnel whose rim has been opened slightly too far. Water from the center and water from the rim no longer arrive together. With Hubble, light from near the mirror's center and light from its outer regions converged at different positions. A star should have appeared as a compact point shaped mainly by diffraction. Instead, much of its light spread into rings and a halo. The mirror's edge was wrong by only a tiny physical amount, often summarized as about 2 micrometers, but the optical consequence was enormous because the telescope had been designed to control light at the scale of wavelengths. To understand how that curve was created, look not first at the mirror but at the measuring tool. During polishing, engineers used a reflective null corrector, or RNC. A null corrector transforms the complicated test of an aspheric mirror into a simple comparison. Light passes through a specially arranged optical system, reflects from the large mirror, and returns to an interferometer. If the mirror has the intended figure and the tester is configured correctly, the interference fringes appear straight and regular, a null. If the fringes bend, polishing is still needed. The RNC used 2 small mirrors and a field lens. Its prediction depended on knowing the dimensions and spacings of those components with exceptional accuracy. The investigation found the decisive setup error inside that corrector. A metal measuring rod was supposed to establish the field lens position through an optical reflection from the rod's end. According to NASA's later safety account, non-reflective coating had chipped from an end cap. The measuring beam reflected from the cap instead of the rod. When the field lens assembly would not fit at the indicated position, washers were added to the retainer. The resulting field lens spacing was wrong by 1.3 millimeters. That number was not guessed from the blurry space images. Investigators found the preserved test hardware, measured it, and calculated that the displacement accounted in detail for the observed amount and character of the aberration. Here is the cruel feedback loop. The mirror was measured against an optical template generated by the misassembled RNC. Each time the real mirror disagreed with that false template, the polishing system removed more glass. Eventually the interferometer showed a beautiful null. It was accurately reporting agreement between the mirror and the tester's wrong prescription. The process did not merely fail to detect the bad curve, it manufactured the bad curve. This is why the mirror was 2 micrometers wrong is only half the story. The failure mechanism was a metrology chain whose reference instrument had not been independently verified after assembly. Precision without an independent check can produce a very precise mistake. There were checks that disagreed. The NASA board reported that an inverse null corrector used during alignment clearly indicated an error in the reflective null corrector. A second null corrector used to measure the finished mirror's vertex radius also indicated a problem. Both results were discounted as faults in those auxiliary tests. The board concluded that the fabrication plan placed complete reliance on the RNC for both manufacturing and high-precision verification. It also noted that simple independent tests against a gross error had been considered and rejected, while cost and schedule concerns inhibited additional checks. Those are the board's established findings. It would be speculation to assign a single person's motive or to claim that one choice alone guaranteed the outcome. Even blurred, Hubble was not useless. Its instruments could still perform observations unavailable from the ground, and image processing techniques recovered some information. But software could not put every scattered photon back where it belonged, especially for faint objects crowded close together. The physical mirror could not be removed and repolished in orbit. Bringing the telescope home was not a practical plan. Engineers instead needed the optical equivalent of prescription glasses, measure the exact error already present, then introduce an equal and opposite error before the light reached each detector. Crucially, they had to trust the correction without repeating the original single reference failure. Two complementary solutions were prepared for the first servicing mission. The replacement wide field and planetary camera 2 included corrective optics inside the camera. For three other original instruments, engineers built COSTAR, the corrective optics space telescope axial replacement. Roughly refrigerator-sized, COSTAR occupied the bay of the removed high-speed photometer. After installation, small mirrors on deployable arms entered the light paths to the faint object camera, faint object spectrograph, and Goddard high-resolution spectrograph. COSTAR did not reshape Hubble's primary mirror. Its aspheric mirrors reshaped the already aberrated beam so that the combined optical system delivered a sharp image. That phrase, equal and opposite, can make the repair sound like one universal lens. It was more exacting. Each science instrument accepted a beam through its own geometry, so COSTAR had to route and correct multiple channels inside a tight orbital package. The 5 anamorphic aspheric mirrors described in the technical record were not ordinary flat steering mirrors. Their controlled surface figures altered the wavefront while the deployable mechanisms placed them into the existing instruments' paths. WFPC2 followed a different architecture because its correction lived inside the replacement camera. Neither approach erased the primary mirror's figure or recovered photons already lost to reflection and absorption. Instead, both made the downstream detector see the combination of two optical prescriptions, the known error in the telescope plus a designed counter-error. The repair therefore depended on characterizing the as-built telescope, not merely returning to the original drawing. The correction was also verified with the lesson of the failure in mind. A NASA technical paper describes 5 anamorphic aspheric COSTAR mirrors made for the 3 instruments and an additional, quick verification technique used during acceptance testing. The engineering details differed among the optical channels, and the correction imposed trade-offs. In the faint object camera, a later performance paper reported lower total throughput in visible wavelengths and a smaller field of view. But the concentrated light improved dramatically. At 486 nanometers, 85% of the point spread function's energy fell within a radius of 0.1 arcsecond after correction, compared with 18% before. This was measured in orbit, not inferred from publicity images. Astronauts installed COSTAR and WFPC2 during the December 1993 first servicing mission. In January 1994, Space Telescope Science Institute comparisons showed the faint object camera restored to planned optical performance. Later instruments were designed with their own internal correction. By May 2009, every active science instrument handled the primary mirror's aberration internally, so COSTAR was removed and returned to Earth. The flawed primary mirror never stopped being flawed. The system became successful because engineers characterized the error, corrected it downstream, and changed how the correction was verified. That is the larger design payoff. Do not confuse one precise instrument with independent evidence. Validate the measuring chain, investigate disagreement, and when replacement is impossible, design the rest of the system around the defect you can measure. The safer process lesson is twofold. Verify critical metrology with a genuinely independent method before irreversible manufacturing, and treat unexplained disagreement as a stop condition rather than convenient noise.